When I was taking AP Chemistry my sophomore year, we were discussing AP Sciences and which one were superior. My teacher joined in. She said advanced biology is basically chemistry and advanced chemistry is basically just physics. And I thought about it for a bit. Ever since I got interested in physics, this statement has been in the back of my mind because aren't all sciences related to each other? If chemistry really is just physics, we should be able to look at the math and logic in both fields to check if chemistry is doing anything physics doesn't already do. If you've taken intro chemistry, you've drawn the Bohr's model. Electron shells orbiting a nucleus-like ring. The energy of an electron in hydrogen according to Bohr is this. This equation describes the energy levels an electron can have in a hydrogen atom. The value negative 13.6 ionization energy represents the hydrogen ground state energy, while N represents the electron energy level. As N increases, the electron moves to a higher energy state, farther from the nucleus, and becomes less tightly bound. This equation doesn't appear out of nowhere. It comes from physics, specifically the interaction between a negatively charged electron and a positively charged nucleus. The same electric force described by Coulomb's law is what creates these conditions for these energy levels to exist. The variables of Q1 and Q2 represents the charges of two particles. In an atom, this is the positive nucleus and the negative electron. Increasing the charge makes the attraction stronger. The variable R represents the distance between them. Because it is square in the denominator, increasing the distance will weaken the force quickly. So the farther an electron is from the nucleus, the weaker the pull becomes. This equation comes from quantum mechanics and the physics of electric forces. The electron is attracted to the positively charged nucleus because opposite charges attracts. That attraction is described by Coulomb's law. For example, this. When an electron jumps in between these levels, it absorbs or releases a specific amount of energy as a photon, and this is where physics becomes chemistry. Chemists use these energy differences to explain why atoms absorb certain colors of light, why elements produce a unique emission spectra, and why even the periodic table has the structure it does. Every element has its own arrangement of electrons, and those arrangements determine how atoms bond, react, and interact with the world. Physics can tell us why electrons have these energy levels. Chemistry uses that information to understand what atoms do with those energy levels. Chemistry class hands you this equation too, but usually without deriving it. You're just told electrons live at these energy levels, and that's interesting. Chemistry is borrowing the physics results, but not deriving it. It's built on top. The actual equation governing every electron in every atom isn't the Bohr's model. Bohr's model is actually a simplification that only really works for hydrogen. The real equation is the Schrödinger equation. This is pure physics, quantum mechanics, and in principle, this one equation contains all of chemistry. Every bond, every reaction, every color molecule, allegedly, is all sitting inside that equation, if you could just solve it. Dirac, the physicist who helped build quantum mechanics in the first place, wrote a line in 1929. He said the physics behind essentially all of chemistry was already understood, and the only issue was that the resulting equations were too complicated to actually solve. That too complicated to solve part is doing a lot of work, and we're coming back to it in a minute. But here's the thing. The moment you go from one hydrogen atom to literally anything a chemist actually cares about, quantum mechanics stops being usable. Not theoretically impossible, but just computationally hopeless. A single water molecule already has 10 electrons all repelling each other, and Schrödinger equation for that system has no exact solution. None. Chemists solve for approximations to it using methods like the Hartree-Fock or density functional theory, and even those need serious computing power for anything bigger than a small molecule. So instead of waiting on physics to hand them an exact answer, chemists build their own layers of equations that are approximate but insanely useful. A few examples is the Arrhenius equation. This is a chemistry equation through and throughout. It's got activation energy, it's got the gas constant, and it's got temperature. But you will not find this exact equation in a physics textbook, because it's a model built to describe reaction rates, not a fundamental law of nature. It works because of the physics built underneath it. Boltzmann statistics show about how many molecules have enough energy to react, but the equation itself is a chemistry level abstraction. It's the same thing with Gibbs free energy. This tells the chemist whether a reaction happens spontaneously. It's thermodynamics. Technically, shared territory with physics, but chemists use it in a way that physicists don't, because it answers the specific question that chemists care about. Will these molecules react and how far the reaction will go? And then there's the whole language of orbitals and bondings that chemistry uses on a daily basis. Hybridization, sp3 orbitals, Vesper theory for molecular shapes, none of us show up by a name in a physics course, even though they're inspired by the same electron behavior that physics describes in the first place. But here is what I think the honest answer lies. It's not that chemistry is just physics. It's that chemistry is what you're forced to invent once physics becomes too computationally difficult to use. There's actually a name for this idea in philosophy of science. It's called emergence. The physicist Philip Anderson wrote a famous paper in 1972, literally called More is Different, where he argued that once you scale up from a few particles to a huge number of them, new patterns show up which are real and predictive, but you'd never guess from studying a fundamental equation alone. Biology isn't just chemistry for the same reason. A cell membrane's behavior isn't something you derive from scratch by staring at the Schrödinger equation, even though nothing about a cell membrane violates it. Compared to units even, physics loves working in joules, electron volts, coulombs, fundamental units tied to individual particles. Chemistry mostly works in moles, molarity, kJ/moles, units built around the Avogadro's number, because chemistry cares about a huge collection of particles acting together, not single particles in isolation. That's not a coincidence. That's chemistry existing at different scales than physics, with tools built for that scales. So is chemistry just physics? In principle, sir, the Schrödinger equation is down there underneath everything, and nothing in chemistry breaks it. But in practice, chemistry isn't physics reverse notation. It's its own set of models. Arrhenius gives free energy, orbital hybridization, built specifically because solving the real physics equations for anything bigger than a couple of atoms is basically impossible.